I warmly welcome you all to this lecture series on artificial intelligence and machine learning. Today, we will explore into an essential concept that powers the learning process in neural networks, that is error propagation, particularly how it operates from shallow networks to deep networks. This topic lies at the heart of training intelligent systems, allowing models to learn from mistakes by adjusting weights layer by layer. We will explore how the error is computed at the output layer and systematically propagated backward through hidden layers, updating the parameters using gradient descent. Understanding this process is important for designing efficient and scalable deep learning system. First, we'll move on to the introduction to error propagation. Error propagation is a foundational algorithm for training neural networks. It works by calculating how much each weight in the network contributed to the overall error at the output and then adjusting those weights to reduce the error. In both shallow networks, you know that what is shallow network? The shallow network means it is with a single hidden layer, and the deep network means with many hidden layers. Backpropagation uses the gradient of the loss function to update weights. It relies on gradient descent and the chain rule of calculus to efficiently compute these gradients, making it feasible to train even complex architectures. And why use backpropagation? The goal of training a neural network is to minimize loss function. So this is the predicted value, this is the targeted value. We have to get the minimized error, which quantifies the difference between the predicted output and the actual output y. This is actual output, this is the predicted y cap is the predicted output. Backpropagation automates the process of finding the gradient of this loss with respect to each weight and bias in the network. This means we don't have to manually calculate how each parameter influences the output. It enables scalable and effective learning for networks of any depth and complexity by using simple local computations. And backpropagation flow overview, this we have seen it in the previous lecture. The backpropagation involves two main phases. What are all the two main phases? Forward pass and backward pass. In the forward pass, we compute the linear combination of, this is the weighted sum of the input, W into A, previous plus B. And we have to apply the activation function sigma of z. This is the sigmoidal function, 1 divided by 1 plus e power minus z, and is followed by the activation function, and a is equal to a sigma of z. After the network outputs a result, we compute the loss. Then in the backward pass, what you are doing is the chain rule is used to propagate the error back through the network. Chain rule we are applying it. The gradient is used to update the weight using the W is equal to, this is the new weight, old weight minus alpha into delta into A, this previous value. In this way we are applying it, where in this case, and alpha is the learning rate, delta is the error term for each layer, error term for each layer, and this would be multiplied by x, and sigma is the sigma, we will use the activation function for this. Next, forward pass example. In this case, if you are taking the neurons, for neuron inputs we are taking it. Inputs what we are taking, input is the x we are going to take. In this x Input is x, weight is w, bias is b. And activation function, any functions we can use, we are going to use sigmoidal function or ReLU function. And z is given by w into x plus b. This is the generalized formula. And the output, if you want to find out, we have to apply this sigmoidal function. It is given by 1 divided by 1 plus e power minus z. We have to substitute the value and we have to find out the value for this. And here the shallow network, that is single layer output, a single output, that means in the shallow network, if you are taking the predicted output, I have the network like this, and this is my output. Each will be connected with each other, and here error target, my target should be 1, maybe 1, and if I am not getting the target, that I can call it as gap, 0.6, error is 1 minus 0.6, so 0.4 will be sent back to the network through backward pass. The true output is y, activation function is given by the z to the power l, and the error is calculated as sigma to the power l, y cap minus y into sigma dash of z power l. And for error propagation to the hidden layers, how we are going to calculate means, for the hidden layers before the output, del L is equal to layer by layer we have to calculate it. W to the power L plus 1 transpose into del to the power L plus 1 into sigma dash of Z to the power L. This del to the power L plus 1 is the error from the next layer. So backward pass. W to the power L plus 1 is the weight from the layer L to L plus 1. And sigma dash Z to the power L is derivation of activation function at the layer L. Each and every layer we have to find out. And the weight updation is after finding out the value WL. This is the new weight. New weight is given by, this is old weight, alpha into delta into a to the power L minus 1. Here many layers we are considering. So we are going to calculate like this. Alpha, you know, learning rate. Del is the error at the current layer. And a to the power L minus 1 is the activation from the previous layer. And the deep networks, that is for the previous example for the shallow network, the single layer, single hidden deep networks means it uses the multiple hidden layers. The generally how we are going to apply means, in deep neural network, error is propagated backward layer by layer using the chain rule. The general rule for layer L, let us take n layers are there, only lth layer I am going to consider. Then the scale del to the power L, W to the power L plus 1 transpose del to the power L plus 1 sigma dash of Z to the power n. And this is the error at the current layer. W L plus 1 is the weight connecting layer. L to L plus 1. Del L plus 1 is the error from the next layer, and sigma dash to the into Z to the power derivative of activation function. How we are going to update the weight? This is the new weight, old weight minus alpha del into a to the power L minus 1. Alpha is the turning date. This is the active a to the power L minus 1 is the activation from the previous layer. And coming into the summary of this slide alone, each layer receives the error from the layer above, adjusts its weight to reduce the total loss. This continues until all weights are updated. If I have n number of inputs back, if we are sending back to front, all weights should be updated. And a complete algorithm summary if you are considering. So first we have to find out the forward pass. This is the weighted sum of the input, WA into B, apply the activation function. Then error, if Y is not matching with Y cap is not matching with the target, we have to send the error back. So that we can call it as the backward pass. Start from the output layer, del to the power L, Y cap minus Y, del dash of the sigma dash of Z to the power L. For all hidden layers, we are going to write like this, del to the power L minus 1, L, W to the power L plus 1 to the power T, del to the power L plus 1, lambda, sigma dash of Z to the power L. And update weights, W to the power L is equal to W to the power L minus alpha into del to the power L, alpha A into L minus 1. So in this way, we are going to calculate the values. So coming into the advantages of the backpropagation algorithm, backpropagation is computationally efficient. In the sense, how we are calling it as efficient and works well for training deep networks. It uses only known values, that is activations, weights and simple derivatives without requiring complex mathematical derivations for each parameter. It is highly flexible, supporting a wide range of architectures like CNN, RNNs, etc. and activation functions. More importantly, it enables effective supervised learning by systematically reducing prediction error. Even though it has got advantages, it has got some limitations too. That despite its strength, backpropagation has several limitations. It is sensitive to the choice of weight initialization and learning rate, which can significantly affect training performance. It also requires many iterations, that is epochs, to converge to a good solution. Backpropagation can get trapped in local minima and saddle points, especially in deep networks. Moreover, it requires that all activation functions be differentiable, which limits the choice of nonlinearities. Coming into the conclusion, backpropagation remains a cornerstone of deep learning, providing systematic way to train networks by updating weights based on output error. It computes gradients layer by layer, computes the gradient layer by layer using the chain rule, making it scalable from shallow to deep architecture. The update rule W is equal to W alpha minus alpha into alpha del into A previous, the previous value. It lies at the, this is the, it bridges the gap between shallow and deep learning network, and it enables the network to reduce loss and improve prediction over time. This algorithm forms the essential bridge between basic neural computation and modern deep learning models. This is very important property of this backpropagation algorithm. Hope everyone understood this basics of error propagation from shallow to the deep networks. The remaining things we'll discuss in the next lecture. Thank you.